Good evening, all of you. Today, I'll be explaining to you how to test for the homogeneity of variance in a group. Okay, so this is my code for that. So, the assumption of homogeneity of variance means that the level of variance for a particular variable is constant across the sample. So, I'll show you that how it is homogeneity or heterogeneity of variance. So, first I'll show you that. Then I will go to the different tests in that. Okay, so just see. Okay, so first let us load the libraries. Okay, so now I am going to read the Excel file golf stats.xlx. I am going to read that to the variable golf. Okay, so now you can just see the golf. Okay, it has got 200 rows and 18 variables are there. Okay, these are the 18 variables. Okay, so I had loaded that Excel file. Now you can see the head and summary also you can see. And now just type summary, you can see the summary of different columns. Now I'm going to plot the graph with x axis having the rank and y birdies. Birdies is particular score correspond to the hitting rate, how the ball reaches the hole, that in the golf. So I'm just going to plot that. X is rank, y is birdies. Okay, I'm going to plot that. So this is the graph. Okay, so here the variance is having homogeneous property. That means, so this is the command for that. You can see. So here I have drawn the linear model also. Okay, to the graph. Okay, and S equal to false means if it is not given false, one layer will come over this line. That's where. So I put that false for that thicker layer not to come around the line. So this is the graph. Okay, I'll show you the equation. So this is the equation ggplot. So here AES I am giving which is x-axis, which is y-axis, and then this is for the scatter plot. Okay, geom underscore point, this tells the scatter plot, and then smooth I am giving LM method LM linear model, and then title. That's all. Okay, so I have drawn that, and you have seen it is. Yeah, you have seen it is homogeneous. Okay, that means the points are more or less similar around the line. Okay, from here to here it is almost similar. That's why it's called homogeneous for the variance. Okay, so now let us see this one. Here I have taken another column events and then birdies. Okay, so see here it is not homogeneous, it is heterogeneous. See, one area it is so many points are there. You are plotting birdies versus events, and this is a model. So this here it is heterogeneous. Okay, this is an example of heterogeneous, meaning that the variance or spread is not consistent across the ranges of values. Okay, so here it is. Okay, dots in the first one, dots are spread out fairly evenly across the line. That is what is meant by homogeneity of variance. Okay, here it is heterogeneous. Okay, so in this case we may want to assess how the number of birdies differ among players who have won 0, 1 or 2 tournaments. Okay. So for that what to do? Okay. Okay. So if you take the golf, this one, you can see one number of wins here. Wins is there. It is 0, 1, 2. It is levels are there. So 0 level, 1 level and 2 level. So it is based on levels. So usually these tests are done on ranks. Okay, this homogeneity of variance tests are done on based on ranks. So let us see how it is done. So I am going to plot the box plot of the wins versus birdies. Okay. So this is the box plot. So what I have done here is that I told it is 0 wins, sorry, 1 win, 2 wins. So the factor has been, you did the factors, you factorize that, or factor, not factor, sorry, factor, you different levels. Okay, so there are levels with 0, 1 and 2. So box plot is based on the levels. Okay, so that's why the factor command came. Okay, and y-axis is birdies. And you have put instead of geom underscore point, you gave geom underscore box plot, so it came box plot. So now what we can see, there is an overlap. Okay, overlap of the box plot. So let us see how it is. You're going to do the test to find birdies where there is difference in the variance between birdies and wins. Okay, so there is a test called Bartlett's test. Okay, that's the first test you have to do to check the. See here, this is giving the explanation of the box plot. So it is telling this box plot illustrates the number of birdies vary widely for players who have no tournament wins. However, players who have 1 and 2 tournament wins have an increasing median number of birdies achieved and less variance. So this is logical, as we would expect players that win more tournaments to have scored more birdies and to be more consistent. Okay, so that's all. So I will again explain you with the figure. So this is a 0 wins. So there is more variance. Okay, see from here to here, more variance is there compared to the 1 win and 2 wins. Okay, that will be natural because those who win tournaments will be having more consistent score. Okay, that's what it is telling. Okay, so now here this command. Okay, what is that command for? Is used to test if k samples from populations are with equal variance or not. Okay, so this Bartlett test is sensitive to deviation from normality. Okay, so here for this Bartlett test, the distribution should be normal. Okay, so let us see how this is coming. You are going to execute that command. So here, so for all the assumptions, the null hypothesis will be there is no difference, or the variance, there is no difference in the variance. So here we go by the null hypothesis because this is greater, this p-value is greater than alpha. Okay, now another test is there, Levin test. Okay, so same birdies and wins, you can see, execute that. This is little more robust. So all these things do the same functionalities, but little more robust, or little more deviation from the normal distribution. This will take into consideration. Okay, so here also the p-value is 0.04. Okay, so we go with null hypothesis. So this one, the Fligner dot test. Okay, this is more. This is actually dealing with non-parametric test. Non-parametric test is nothing but a distribution that is not normal distributed, that is called a non-parametric test. Okay, or this test is done for the to double check for the previous parametric test. Previous two tests deal with the normal distribution, and this test, this Fligner-Killeen test, okay, this test deals with non-parametric or non-normal distributions. Okay, so this is a command for the Fligner.test, and let us see that. Okay, so you get p-value as 0.02. So if you are taking alpha value as 0.01, you go by the null hypothesis and say there is no difference in the variance. Okay, okay, I hope you understood. So here also from this figure, from this box plot, there is overlap is coming. Okay, that is why there is no much difference in the variance. Okay, there is overlap. Okay, overlap is coming. So now I will explain in detail this Fligner-Killeen test. Okay, so I will, let me see how much time I have taken. Yeah, 11 minutes only, so I will explain this also in the same one. Okay, so this is the code for that. So this Fligner-Killeen test is a non-parametric test for homogeneity of group variance based on ranks. Okay, ranks means factors. Okay, I told you when we took the wins, it was in 3 layers: 0 win, 1 win, and 2 wins. That's what based on ranks. It is useful when the data are non-normal distributed or when problems related to outliers in the dataset cannot be resolved. Okay. So we take null hypothesis, all populations variance are equal, and alternate hypothesis, at least 2 of them differ. Okay. This is syntax. Okay, I showed you just before. You have to give a formula, which versus which. This is a formula and the data set. Okay, values versus tilde. You have to use the tilde command. So let us take there are inbuilt data sets in R Studio. So here I'll be using plant growth. I'll show you that. I hope you understood the formula and the main use of Fligner-Killeen test. Actually, one person had commented in my channel to make this video. That's why I'm doing this. Okay, so let us. Okay, so this is the plant growth. So it has weight and group. So these are ranked. Okay, these are ranked. The 3 groups are there. Just type structure. You can see 3 levels are there. The weight is numeric and this is a factor with 3 levels. Okay, so let us do the box plot. Okay, and see how it is. Box plot command is box plot weight, and then I have to use the factor command to group that. Okay, this command. Okay, this is a box plot command. Okay, so let us execute that and see. Okay. So I got the box plot. So you can see variance, there's overlap. Okay, so there's no much difference. So let us see the result. I mean Fligner test and see. So here the command is, as I told you, Fligner.test weight versus group, and data set is plant growth. Okay, and let us see that. Let us see what is there in the result. I have put in the result. So here it gives you 0.3. So this is much greater than alpha. So there's no much difference in the variance. Okay, same thing what we got from the what we could deduce from the box plot. Okay, now here we did 1 versus 1. Okay, suppose we have got two independent variables. Okay, multiple independent variables. So what to do? So there is a data set tooth growth. Okay, so just you can see there are supplement and then dose and then length of the teeth. Okay, so there are three variables are there. So you can take length versus these two dependent variable. You can make length len and independent variables supp sub and dose. Okay, so when we have got two independent variables, what to do? That's what we are going to see here. You have to, there's a function interaction. Okay, if you, so inside interaction you have to give the independent variables supp comma dose and len. That's the dependent variable. Okay, these two are independent variable. Okay, so let us see how we are going to do that. Okay, so I'm going to do this, and then let us see the result. Okay, so here same, there's no much there's no difference in the variance because this p value is 0.1706. Okay, now you can, there's another inbuilt database is known as insert sprays. Okay, see here, this is insert sprays, 72 rows are there, count and spray. Okay, so let us do a Shapiro-Wilkinson test to see whether it is normal distributed or not. See, the p-value is very low, so it is not normally distributed. Always they ask H0 or our null hypothesis, it is normal distributed, but the p-value is very less, so it is not normal distributed. That you can check with the histogram also. It is not normal distributed. So we are going to plot the, see, to get the box plot, you can either use plot command or box plot command. Okay, here I am using plot command. So see, here you can see there is difference actually. These are coming entirely below these three, so there should be difference in the variance. So I use the plot command. So same, if you use the box plot also, you'll get the same thing on same figure you get. Now I am doing the Bartlett test first, and you can see the command for that. Same, there's no much difference. Okay, I'm doing the three tests. The first two. I mean, this Fligner dot test we use to double check the results of this. Okay, these two are actually for normal distribution. Okay, so there's no point in doing that in this because this is not at all normally distributed as you saw from these two commands. So we'll do this one directly. Okay, I'm doing this one 0.01. Okay, so suppose if your alpha value is 0.05, so you will reject the null hypothesis. So the same thing. Okay, okay, so there is difference in the variance. Okay, so I will show you one more example. I am making a vector here, size and the location. So, and then I'm going to make a data frame from that, and then box plot that, and then I'm going to do the test and see. Okay, let us see that. Okay, so this is one vector, another vector, and I'm going to combine both the vector and make a data frame, and let us see that. Okay, let's see that. So I'm making a vector and then location and the vector. I'm combining that. Now let us see what is there in that data frame. So 30. Here 30 numbers were there. I made repeat of 10, 10, 10, 10. Okay, so forest A 10, forest B 10, forest C, that's why 30. Okay, so now I'm going to plot the box plot of size versus location. Okay, after making the factor. Okay, let us see that. Okay, there's no much difference in the variance. So let us see whether we are getting that. When we use the Levin test, so Levin test is in the car library. Okay, you have to load the car library, then only we get that. So 0.5, we go by the null hypothesis. So let us double check with this again. So this also gave 0.6. Okay, one more example I have put here. So I will show you that. So here I am making x1, s2, s3, and GL command is for making levels. Okay, so what is it? I want 6 levels I want with the repeat. So 1, 1, 1, 1 will come, 2, 2, like that 6 times, 3, 3. So let us see that. So here 1, 2, 3, 4, 5, 6. So 6 are there, that's why 6 times. Okay, that's it. This one 6 has come. Let us see that. X1 I made, X2 I made, X3 I made. Okay, so X I am making. So suppose if I type here X and C. Okay, so 1 6 times, 2 6 times, 3 6 times. Okay, levels. Okay, GL command is for making levels. Okay, and then Y I am combining X1, S2 and S3. Okay. Okay, so I am plotting Y versus X. Okay, you can see this is a box plot. You can see this is very much below this one. So there should be difference in the variance. P-value is very less. So you reject the null hypothesis. Here also P-value is very less than 0.05, alpha 0.05. So there is difference in the variance. Actually, these two have more or less similar variance, but this is what difference. This is the difference. Okay, I hope you understood. If you got any doubt, you can just comment on that and we'll try to explain that. Okay, thank you.